Okay, cool. So thanks everybody for having me. As I'm really happy to give this talk. So today I'm going to talk about connections between, like Andre said, between computational complexity theory and also algebra and combinatorics, kind of in the intersection of all three. So this is based on what I'm going to talk about today is mostly based on a paper from last year with Susanna de Resenda, Robere, and Jakob Nordstrom. But a lot of the work that's appearing in this talk has been work of mine that is kind of the culmination point of a lot of works in the past. So I'm going to be talking about a fair bit of stuff. So okay, so to begin, so this talk's going to be about propositional proof complexity. So this is a subfield of computational complexity theory, which has lots and lots of nice connections with combinatorics. So the main question that we kind of ask in propositional proof complexity, which is how hard is it to prove theorems? Okay, so this is kind of a stupid question. We're mathematicians. We would expect that we're kind of the experts on how hard this would be. But what we're actually kind of interested in is sort of formalizing this question very rigorously. So to make it less stupid, we can say, let's fix a propositional tautology, tau, say. So only over propositional logic. So, we have and, or, not, and, some Boolean atoms like 0, 1. And let's fix a propositional tautology and also fix a formal proof system, P, for proving tautologies. So a very natural question to ask, I would say, is what is the length of the shortest proof of T in this proof system? Okay, this is naturally like a complexity theoretic question, right? So I give you a tautology. How hard is it to prove a tautology? And this is a very interesting problem at the nexus of kind of a lot of things. So when you think about it, the key sort of thing happening here is the syntax of the proof. Because if you think about it semantically, what's happening, I mean, it's a propositional tautology, so semantically it's equivalent to true, right? It's the constant one. So I have many, many different ways of representing one true syntactically. And some of them are extremely easy to prove, and some of them are very difficult to prove. So like, what's the minimum number of symbols you need to write down a proof depending on the encoding, the particular encoding of one that I chose? Okay. So propositional proof complexity as a field kind of grew out of the intersection of logic and also complexity theory in the early 90s. So there's what's considered what's considered the formal basis of propositional proof complexity, even though there's like a number of papers that happened before that, is this paper from '79 by Cook and Reckhow. And they basically initiated the study of this question. And kind of the main results for complexity theory that you take away from this paper is the following. So if you can prove that for any proof system, there's some family of tautologies, so T of n, which n think of as going to infinity, so some infinite family of tautologies, such that T of n requires super polynomial size P proofs, then NP is different from co-NP. And if you're not familiar with complexity theory, well, probably you know that that just means then you should know that implies that P is different from NP. So Cook and Reckhow originally introduced this as maybe a natural line of attack for proving NP different from co-NP and therefore P not equal to NP. So consider different families of propositional proof systems, stronger and stronger and stronger ones, and try and prove lower bounds on them. So this you could call to be like sort of the program of proof complexity, if you like. So prove lower bounds on stronger and stronger proof systems, identify families of tautologies which are complicated, and which are hard to prove, sort of like difficult representations of one. And then over time, maybe we can develop techniques that will actually allow us to grapple with, NP versus co-NP, which is kind of one of the main open questions, like one of the central open problems in computational complexity theory. So while this was the genesis of proof complexity in a complexity theoretic sense, now there's been like tons and tons and tons of connections with lots of different areas. So proof systems in theoretical computer science, and of course in every field of mathematics, come up very naturally, right? And it turns out that in many areas of mathematics, including combinatorics, which is what we'll talk about today, there's the complexity measure of like what is the shortest proof turns out to have a very, very natural meaning in lots and lots of different fields. And so now there's lots and lots of rich connections between proof complexity and lots of other areas. So things like algebra, optimization, geometry, particularly polyhedral geometry, even things like cryptography, circuit lower bounds, and the list kind of just goes on and on and on. Okay, so here's a diagram, I guess, of it's updating. Okay, here we go. Here's a just sort of like a collection of some proof systems. You probably you don't need to worry about what they all are. I'm not going to define them all for sure, but here's just some of the proof systems that we study in practice. So typically in proof complexity, we divide the proof systems up into sort of Boolean proof systems, which we think of as using like standard propositional logic, like and or and not, kind of normal deduction rules like modus ponens and things like that. We have algebraic proof systems, which fundamentally they study like provability using polynomial equations and like systems of polynomial equations and deducing new polynomial equations from old ones. So there's many natural connections with things like algebraic geometry here. And then finally, this third class that we typically study is usually like semi-algebraic systems. And by this, I mean, we're studying polynomial inequalities over the reals. And so you can probably imagine that these proof systems over here, they have lots and lots of natural connections to problems in geometry and also optimization, right? Because many, many algorithms in optimization can be like rephrased as searching for a short proof, right? In some sense, this is exactly what linear programming is doing. You're probably like, some of these proof systems are, oops, there we go. Some of the proof systems, you probably don't recognize all of the proof systems here. Maybe you recognize some of them. Probably you're going to recognize the Nullstellensatz proof system, which is what I'm going to be talking about today. The resolution proof system, maybe you've also seen. I've also put, probably the most familiar proof system that everybody here should be familiar with, which is a ZFC, right? ZFC is normally stated as a first order logic, but of course you could just imagine using it like propositionalizing proofs in it and imagining like proving statements in it. And of course we can easily verify ZFC proofs. So, it's a perfectly valid proof system as far as proof complexity is concerned. And this is also quite interesting when you think about, the fact that in order to prove NP not equal co-NP, we have to prove that for every proof system, there's some family of tautologies that's hard. So even for things like ZFC, we have to prove that there's some weird family of tautologies that require super long proofs. Okay. So primarily, we're kind of interested in proving lower bounds. Okay. So what's known? I mean, on this diagram, I can kind of sketch the line that's known for what proof systems we have lower bounds. So in general, if you go below this into this yellow area down here, we're able to prove lower bounds on all of the proof systems here. Also, this diagram is very far from being complete. Like I just picked out a few of the most powerful ones I can think of. There's many subsystems and other interesting systems that we consider here. So in today's talk, we're going to focus on one of these.
Robert, just two small questions. So first, arrows here mean is that one is strictly weaker than the other, or
yeah, that's right.
weaker than the other.
Yeah.
And the other thing I wanted to ask you, I guess you'll give an example at some point, but I think for some people it would be helpful just to, I'm not sure that everyone have seen proof systems before.
Yeah.
So it would be helpful to see some really basic example of that.
Yeah, we'll see that actually like in a slide or two. Yeah.
Okay, great.
Yeah, so we'll see some examples of proof systems in a second. So let me say, so when I say a simulation, like a simulation here, what I mean is like basically any proof in the system below can be like written as a proof in the system above. So like in an efficient way. So you don't, you can represent any resolution proof as a Frege proof, for example, without losing any efficiency. So today I'm going to talk about
by efficiency here means the length of the proof, right?
Say it again. Yeah, efficiency means the length of the proof.
Okay.
Yeah. Okay. So today we're going to talk about this Nullstellensatz proof system, and we'll see lots of examples. So this is kind of a nice proof system because you don't really need to know lots of proposition like proof theory in order to understand what's going on, because probably you might be familiar with it from algebra, right? So the Nullstellensatz proof system is just, the definition is basically just inspired by Hilbert's Nullstellensatz from algebraic geometry. So I'll state it here, okay? So let's let F be any field and consider any collection of polynomials over F, okay? Say we have M of them, okay? Well then Hilbert's Nullstellensatz says the following. It says that this system of equations, the system of polynomial identities, P1 through Pm, has no solutions in the algebraic closure. So in other words, this is like an unsolvable, they have no common root, there's an unsolvable system of equations. If and only if there are some polynomials, some other polynomials, Q1 through Qm, such that if I multiply all of these guys together, if I multiply the Pi's by the Qi's, and then work it out syntactically over the field, I get 1. Okay, so what's going on here? I mean, I think that oops, sorry, we are going a little bit too fast. There we go. So the forward direction here, oh, sorry, I should do it this way. The backwards direction here should be pretty much immediate, I think. So suppose that you had a solution to, suppose that you actually had one of these solutions, right? If you plugged in a value that actually like resolved all of these things, that satisfied all these things to 0, and suppose that these set of polynomials existed, well then plugging in that solution into this representation right here would give you 0 equals 1, which is obviously impossible, right? So clearly, if some of these polynomials exist, then this system is going to be unsatisfiable. Like there's not going to be any common root. The surprising thing is that, in fact, this is like a complete method of proving that this is unsatisfiable. So if there is no solution, then in fact there is there's always going to exist a family of polynomials for which this is true. So this is like a quintessential example of a proof system, right? It's a syntactic representation. It's a proof that things are unsatisfiable. Normally it's stated in a totally algebraic language, but I like to think of this purely as like a proof, as a totally, it's a relationship between a syntactic object, which is this proof, and a semantic object, which is like determining whether or not there are points that satisfy all these equations, right? So I want to think about, even though many of you might have seen the Nullstellensatz before in like algebra and geometry, I want to think about this as a proof system in that sense. And I hope that that's sort of clear. And this is also how it's interpreted in that, but I really want to sort of emphasize that point. So with that, I'm going to give you a definition right here. So if you give me any set of polynomials over the polynomial ring associated with the field, then I'm going to define a Nullstellensatz refutation of these polynomials to be any list of polynomials such that this is true, such that this condition is true. And it's a refutation in the sense that it's literally a proof that these polynomials cannot simultaneously vanish over the algebraic closure of F. Okay, so let's see an example, like a super concrete one. And to be even more concrete, let's just to remove the algebra from the picture, if you're not comfortable with it, let's like think about Boolean logic instead. So here's a Boolean formula. It's clearly unsatisfiable, right? It says, okay, x1 has to be true. Think about all of these xi's as being either true or false. Okay, so it says x1 has to be true, and if x1 is true, then x2 is true, and if x2 is true, then x3 is true, and also x3 is false. So this is clearly unsatisfiable, right? So we should be able to refute it. Okay, well, we can refute it in Nullstellensatz. The first step is to actually encode these things as a system of polynomial equations. So here's the most natural way, I think, to encode it as a polynomial equations. So, you know, x1 is true means x1 equals 1, right? This guy right here, either x1 is true, so x1 is 0, or x2 is 1, right? And then that's going to be satisfied, and then so on, all the way through. And now, in order to, since we're working over a field, you know, we're not guaranteed that down here these guys are going to be constrained to have 0, 1 values, right? So we're also going to add in some extra polynomials which just ensure that that's true. So for every variable, we'll add in this xi squared equals xi variable, and all this, I mean, the only solutions to this are 0 and 1, right? So this just ensures that we're actually dealing propositionally with things. Okay, cool. So now it's also important to note that intuitively, what these extra equations give you is multilinearity. And by that, I just mean, what is this really saying? I mean, it's just saying that xi squared equals xi, right? Or in other words, like xi to the d equals xi, right? So in all the polynomials that we're going to be manipulating, we can, without loss of generality, thanks to these equations right here, assume that, you know, the individual degree of any variable is going to be at most 1, because we can always use these to basically kill all the higher degree terms. So that's the intuition for keeping, that's like the algebraic intuition thing for keeping these things around. Okay, so now let's actually give a Nullstellensatz refutation of these things. So, well, I'll just sort of write it out for you. So the polynomials in red, these are going to be the GIs, like the extra polynomials that I'm going to multiply by the guys, right? And so if you just work this out, right? Well, I mean, if I look at x1, x2, and x1, x2, well, then I have x3 and 1 minus x3 right here. So those are going to cancel out to give me x1, x2. And then now I can factor out x1, and then I'll, again, sort of cancel out the x2 and the 1 minus x2. And then finally, we're left with 1 minus x1 equals plus x1 is 1, and so that's just 1, right? So to be totally formal, these polynomials, q1 equals 1, q2 equals 1, q3 equals x1, and q4 equals x1, x2, this is a Nullstellensatz refutation of this system. And in fact, this works for any field, right? Like I didn't even use any particulars of the fields when I did this calculation here. Okay, cool.
So just I guess you'll actually next slide is going to tell us what is the size of the refutation, right? So I'm not going.
Yeah, right. Yeah. Okay, cool. Yeah. So now that we have a proof system, we have to we're interested in proof complexity. So we're interested in like complexity measures, like actual measures of how complicated the proof are. And these are the two complexity measures that we'll be dealing with today. So I'm going to call the degree of the refutation, if the refutation is the sum pi qi, the degree is going to be the maximal degree of any one of these product terms. Okay. And this is because, this is before cancellation intuitively, right? Because once I expand this out and work it all out, it's going to be equal to 1 anyway. So measuring the degree after doesn't really make sense. So the the intuition here is that, like, if I was an algorithm and I was given this representation, I was given a list of these QIs and told it was a proof of P of that these PIs were unsatisfiable, I would have to actually go and, like, you know, work out the algebra, right? Like, I would have to multiply through all the things and expand everything out. And it's hard to avoid, like, multiplying out all the polynomials. And so I'm going to have to pay intuitively for up to the degree for all the monomials that are going to occur. And also I'm going to have to, because of this big expansion, I'm going to have to, like, evaluate every single monomial before cancellation that's going to occur in this term when I do it naively. So the degree of this refutation I'm going to define to be the maximum degree of an individual product. And the size of the refutation is going to be the total number of monomials that you get when you expand this out before you do cancellations. So just imagine, like, doing all the maximal expansion out of these polynomials, fully expand them out, and don't cancel anything. Don't do any subtractions or anything to cancel them out. And then you'll get like a gigantic list of polynomials. Many of them will be repeated. And then we know that once we sum them all up, it'll all cancel out and you'll just be left with the constant term 1. And just to say it again, the intuition for measuring this to be size is that any, like, algorithm, like, intuitively, if we want to verify this proof, we would have to multiply it all out. So this size is, like, representing how much work we have to do in order to actually evaluate that the proof is correct. Okay. So just to go back to this proof that we just saw a second ago, I mean, the degree of this thing is clearly 3. So here, instead of working it out step by step, I just expanded it all completely, right? So the degree is 3 because we have a monomial of degree 3 right here. And the size is 7 because we have 7 monomials before we do cancellations. And then you can see that everything just gets canceled out. That's not the one term. Okay, cool. Okay, so today, the sort of results I'm going to talk about today, these are going to be size degree trade-offs for Nullstellensatz. Okay, so what do I mean by that? I'm going to give some natural systems of polynomials that are going to satisfy the following. So first, they're going to have some Nullstellensatz refutation in some degree t, which you should think of the degree as being very low, and some size s, which you should think of as being very large. Okay, and then there's going to be another system of refutations for these Nullstellensatz proofs, which have much higher degree than my first one, but when I can trade that off, this higher degree, by making the sizes of the proof much, much smaller. And then finally, if I take this refutation with the high degree and the low size, if I decrease the degree by even a little bit, this is going to incur a gigantic blow up in size. Any proof that has even smaller degree than T2 is going to have to pay by blowing up the size like a lot. Okay, and the way that we're going to do this is actually, I think, quite novel. We're going to give a combinatorial characterization of Nullstellensatz proofs for this particular family of polynomials. So we're going to give a really nice equivalent description of what an algebraic object looks like in terms of a purely combinatorial object. Okay. So I think that this is sort of like a very natural goal to ask about. I have 2 complexity measures. It's very natural to ask, like, how do these 2 things relate? Can we actually trade them off? Right.
So just actually, Robert, can I ask a question? So when one does all these reductions between different proof systems, what would it mean actually to reduce, say, something to this Nullstellensatz proof system? What restrictions do you put typically on the degree and the size?
Right. Good. So usually, when I wrote the thing on the slide before, all the reductions were efficient with respect to size. And so degree is going to turn degree for these algebraic proof systems turns out to be a very natural complexity measure because optimizing degree often lets you, like, optimize size. Like, I'll mention this later, but, like, if I know that I have a proof in degree D, well, then I can just generate all the monomials up to degree D, of which there are n to the D of them, And then, that's going to be a proof of small size if the degree is also small. So this is a natural measure in that sense. All of the earlier simulations that I mentioned a second ago, these are all efficient with respect to size. And this is why, actually, I'm going to go to this next slide, because this is a perfect segue into this. So all of the polynomial systems I'm going to consider today, and in general in proof complexity, we always start with usually, instead of working with tautologies, we work with contradictions. This is just like a convenience thing for technical reasons I don't want to get into. But the reason that we're going to work with, like, specifically, when we work with contradictions, we're going to be working with contradictions that are in a very simple Boolean form, CNF formulas. So these are just going to be ands of ors of literals, okay? And the reason that we do this is because this is a very simple representation of a tautology, first of all. And since it's simple, it means that, like, every proof system, basically, that we consider can manipulate it. Because you get some proof systems which are very weak, and the types of objects that they can manipulate becomes very, very weak. So we kind of, in order to be fair, in order to give a fair comparison of the strength of two different proof systems, we kind of have to give them all the weakest representation, which is also sort of efficient, right? So when I showed you this earlier thing with respect to size, this earlier simulations between the proof systems, this was all for CNF formulas. We always measure the size because this is kind of like putting them all in the same playing field. So hopefully that answers the question. So
it's like this general state exams in mathematics. You want to get the simplest exercise.
Right. Yeah, exactly. Yeah. And it's kind of interesting, actually, because there's just sort of a follow-up on that. Like, it's kind of interesting because for many of the like, if you give me any tautology, I can, of course, rewrite it as a CNF formula. Even if it's a complicated Boolean formula, I can rewrite it as a CNF formula without blowing up the size very much. And so it's also a complete representation in that sense. And yet we still don't have good examples of, like, really hard to prove statements, which is kind of interesting. Part of the reason why we don't have lower bounds for a lot of these stronger systems is simply that we don't know any tautologies which are hard for them. A very natural example of one, which is like one that I really like, is a propositional encoding of, like, the fundamental theorem of algebra, like saying, like, a polynomial has exactly d roots. You can encode this propositionally, and we don't know how to give efficient proofs of it. The best thing we know how to do is to just enumerate all the points. But that's a bit of a digression. So all of the polynomial systems today, as I said, are going to come from these Boolean formulas. And so since we're dealing with Nullstellensatz, we have to convert them to polynomials. We already saw how to do that. But just to say it again so that we're all on the same page, if I have a clause of which this function, this formula f is going to be a conjunction of, well, then I can convert it to a polynomial just by doing sort of the natural thing, right? Like, for every positive literal here, I'm going to replace it with a 1 minus x term. And for every negative literal here, I'm going to replace it with an x term. And now this clause is going to be satisfied if and only if, like, this polynomial expression vanishes, right? And then again, to ensure that all the solutions are going to be 0, 1, I have to add in these extra xi squared equals xi polynomials in order just to sort of constrain our range. And it's good to notice that this is a field-independent encoding. So, like, this is kind of a universal encoding. It goes back to the principle of, like, making everything as fair as possible. I don't need to do anything field-specific. It's all sort of fully general. Okay, cool. So now I can state the main result with there will be some definitions that I'll say in a second, but we can at least state it. So here's the main theorem. And so for any good directed acyclic graph G, and I'll say what good means in a minute, and for any field F, there's going to be a Nullstellensatz proof of a certain family of Boolean formulas, which I'm going to call Peb sub G. It's going to be called the Pebbling formula, that has degree D and size S plus 1. if and only if there is what's called a reversible pebbling strategy for this graph G that uses exactly D pebbles in time S. Okay, so this is a connection between an algebraic proof of a particular formula with a strategy in some sort of combinatorial pebbling game on the graph G. And it's a very, very tight correspondence. So we have time S, and the time and the size and the degree and the D are tight. They can be attained simultaneously. So if I have a proof with degree D and size S here, then I have a strategy using D pebbles and time S down here. And so what this means is that, if I can prove any trade-offs for combinatorial pebbling, which, combinatorial pebbling games appear all over the place in the literature, and there's lots and lots of trade-offs that are already sort of established for these things. These will be equivalent to trade-offs for Nullstellensatz. Now let me actually define what the things that are missing here in this statement. Okay, so first of all, let me tell you about what these pebbling formulas are. So a directed acyclic graph G, I'm going to say it's good if it has a unique sync vertex. That's it, just one sync. Okay, and then now if I have any good directed acyclic graph, then peb sub G for the pebbling formula of G is going to be the following unsatisfiable Boolean formula. It's going to be in CNF. So I'm going to have a Boolean variable for every vertex in the graph. And then the clauses are going to have, there's going to be two types of clauses. So first, if I take the unique sync vertex T, I just have the unit clause that says T is false. Okay? And then second, for every vertex U, including the sync vertex, what I say is that if the predecessors of U are all true, then U is false, or then U is true, sorry. Okay, so intuitively, what does this mean? Well, what it means is that, here's a simple example. Here's a good graph. It has exactly one sync vertex. It's like a little pyramid graph. Okay, so if you write it out, what do you get? Well, you get that the sync is false, right? For all the source nodes, well, they don't have any predecessors, so they just turn into these clauses down here that say, okay, well, the source nodes are true, right? So the source nodes are true, the sync node is false, and then if I have two nodes that are sort of connected in a thing, and the sources of that thing are true, then the conclusion is true. So if you think about it, what is this saying? Well, I'm saying that everything here is true. If these guys are true, then these guys are true, which means that this guy is true, but this guy is false, which we've hard coded into the formula. So it's actually a generalization of the earlier simple guy I showed you before, where x1 was true and x1 implied x2 and so on. And intuitively, all this is it's like encoding, like you could call it modus ponens if you wanted to be fancy, right? Like this is a refutational encoding of like implication. So if A and B are true and A and B imply C, then that means that C is true, right? Okay, so that's it. That's all that these PebGs are. So now, what is this reversible pebbling game? Okay, well, the reversible pebbling game is a simple combinatorial game that we play on directed acyclic graphs. Okay, so how does the game work? Well, we have an unlimited collection of pebbles. Okay, so now our goal is to get a pebble onto the sync of the graph and then clean all the pebbles off of the graph. So in general, we're going to be putting pebbles on vertices by some rules and then taking them off. And then our goal is to somehow get a pebble to the sync of the graph and then cleaning all the pebbles off of the graph. And then the allowed move that I'm allowed to do, there's one move and it's symmetric. So if the move is just the following, if every immediate predecessor of a node in my graph has a pebble, then I'm allowed to either place a pebble on U if it's not there, or if there is a pebble there, I'm allowed to remove it. Okay, so let's see an example just to, oh, don't know why that happened. Okay, so here's a simple path graph. Okay, it's on 5 vertices. So we want to put a pebble right here. For some reason, the first node is disappearing. We want to put a pebble right here. Now, we can start by, I don't know why that's happening. Okay, so we can start, we have to start with the source nodes, obviously. For the source node, all the predecessors of the source node have pebbles, vacuously, because there are no predecessors. So at any time, we can put a pebble on the source node. Right, like that. And now that there's a pebble on the source node, well, I can put a pebble on the next node, right? Because now all the predecessors of this node have been pebbled. And then, now you can just see that you can just continue placing pebbles down the line like that. So I can place a pebble on this node. There we go. And then I can place a pebble on the next node. And then I can place a pebble on this node, and then I'm done. Right? And now I need to clean the graph off. I need to clean all the pebbles. So all I'm going to do is I'm just going to run the thing in reverse. So now, like this node, now like if I have a pebble on this node at this time, all of its predecessors have pebbles, so I'm allowed to remove this pebble on that node, for example. So now we can go there, and then we clean it off, and then now the whole graph is clean. So in total, well, we used 5 pebbles. Sorry, just waiting for it to catch up. There we go. In total, we used 5 pebbles in order to do this. And the length of time that this pebbling strategy took was 10 steps to get a pebble to the last node and to clean it all off. Okay. So it's natural to ask, can we use less pebbles? Right? Well, of course, there's a way to do it. So how do we do it? Well, I'm going to start as before by placing a pebble. Oops, sorry. There we go. I'm going to start as before by placing a pebble on the source node. Okay. Then I'm going to place a pebble on this node right here. And then I'll place a pebble on the third node. Now I'm going to start removing them. So if I look at this guy right here, well, his predecessors are all pebbled. So in order to minimize the pebbles, I'm going to start removing them. So, okay, so we pull that guy off. And then we pull off the first one. And then now we're left with a single guy right here. And now we can just continue and pebble it to the end, right? So now we just pebble that node, and then we're done, except having to run the moves in reverse again to clean the graph off. So, this is a perfect example of the kind of trade-off I was talking about earlier. In order to get a pebble to the sink this time, we used only 3 pebbles. But of course, the trade-off was that we had to increase the number of moves that we had to do. So less pebbles, but more time, right? And now you can probably already imagine how, like, the kind of connection.
I'm sorry.
Yeah.
So this number of pebbles is the number of pebbles on the last step where you get
the number of pebbles is the total number, like the maximum number of pebbles you had to use at any step.
Okay.
Yeah. Yeah. So, So when I say this, so when I say what is this reversible pebbling number, I mean, if you give me that number of pebbles, I can get a pebble on the sink node. So like I only need to use that many pebbles at worst over any of the steps of the strategy. Yeah. So now you can probably imagine what the connection is going to be with Nullstellensatz refutations. We're already kind of seeing it, like intuitively the number of pebbles is going to somehow end up corresponding to a degree, and the length is going to correspond to size. So just to kind of say a bit more, if you look at this path graph of length p sub n, like I said, of just taking 5, well, you can prove with not too much difficulty that you can actually get a pebble on the sink with using only order log n pebbles. And it's a nice exercise to do that. Maybe to see a different graph, one that's not so simple, so that it doesn't have like in degree 1. Here's our pyramid graph again. So we want to get a pebble on the sink. So how do we do it? Well, we start by putting pebbles on the source nodes. Now we can pebble the next guy because all of his predecessors have pebbles. Oh, is there a question? Oh, no. Okay. now we can start, in order to sort of minimize the number of pebbles we use, we can start removing things, start adding pebbles on the other sources, work our way up, start removing these guys, and then finally get a pebble on thing, and then reverse the whole strategy in order to clean the graph off. And then this time, you can see that we used 4 pebbles, and the time we used 18 steps. In general, if you have a height h pyramid graph, so here's a height 4 one, then it turns out that the reversible pebbling number is theta of h. So it's roughly h. The lower order term is actually kind of a fun, working out the lower order term is actually a fun exercise too. So, okay, so where did this game come from?
Robert, just a small question. So why would we need to clean up the graph if it looks like always is just twice the time? Kind of.
Yeah. The meaning for that will be revealed later in the talk. Okay. It's true. I could have just defined it as getting a pebble on the target and then just stopping and cleaning it off. It turns out that when we're measuring Nullstellensatz proofs, it'll be twice that number. So I'm just going to say reversing it.
To be more natural, kind of.
Yeah, it's just a more natural. More natural correspondence. That's it. Yeah. The other thing too is that when you're cleaning pebbles off the graph, if you want to compose 2 strategies together, it's a very natural thing to do. Like if you could imagine pebbling to a node and then cleaning off the entire graph, and then now I can start from here and then pebble the rest of the graph. Having no pebbles anywhere else makes a lot of sense, right? Yeah. Okay. Cool. So where did this pebbling game come from? Well, it was introduced by Bennett, and his original motivation was to study what he called reversible computation. So this is like computation where computational models where if I can transition from one state to the next state, then I can also transition from that state back. So it's kind of an energy efficient. His motivation was sort of energy efficiency. But it turns out to have sort of tons of applications in time-space trade-offs and other lower bounds in complexity theory. So back in 2013, there was this line of work that used to prove space lower bounds, so the amount of memory in computation. And also, if you looked at this combinatorial pebble game and you thought maybe it's not that hard to look at a graph and just sort of calculate what the number should be, like maybe there should be some greedy algorithm that works. Well, it turns out it's actually really hard to calculate the number. It's in fact p-space hard even to approximate this number. So this is more difficult than NP hard if you aren't familiar with complexity theory. So in proof complexity, where do these things sort of come up? Well, I mentioned this earlier, but if I have a degree D Nullstellensatz refutation, well, then this immediately tells me that I have a size into the D Nullstellensatz refutation just by deriving all the low degree monomials. This isn't tight because, if D is order n, then this is not a very good upper bound, but of course you can improve the upper bound in the normal way. These pebbling games, however, turn up in tons and tons of other trade-offs in the literature. So for the resolution proof system, which I haven't defined, but is kind of the simplest Boolean proof system, there's a really long line of work proving different kinds of length and the analog of length and degree sort of trade-offs for resolution. For a system that's slightly stronger than Nullstellensatz, there's also some other very limited trade-off results known, but in general, the techniques aren't sort of as well developed. And in particular, our results are the first results for Nullstellensatz, and other results use these pebbling formulas and this reversible pebbling, but their characterization isn't nearly as tight. Like what we're going to give today is like an exact correspondence between these proofs and these games, which I really think is kind of a cool observation, especially considering that this game has come up in so many different contexts. So what other results are known about this pebbling numbers in proof complexity? Well, it was proved already 20 years ago that if you looked at these pebbling formulas, then the degree was at least they proved that the degree was at least what's called the black pebbling number. This is like reversible pebbling, except you can always take pebbles off. So you don't need to have all the predecessors being pebbled in order to remove them. Okay. So this is a weaker lower bound, because clearly the black pebbling number is going to be lower than the reversible pebbling number, because I can obviously save if I don't have to have all the predecessors there all the time. A second result from just a few years ago by Siumanchan proved that if you take just a decision tree, which is like probably people are familiar with what a decision tree is, well then refuting these pebbling formulas by a decision tree, any such decision tree that does this is going to have depth at least the reversible pebbling number. So this was considered sort of like a strengthening of the kind of results that were out there. And then actually a few years ago, implicitly in a paper that I was a part of, we proved that any Nullstellensatz refutation of these pebbling things have degree at least the reversible pebbling number. But we didn't prove the tight correspondence. And I'd like to point out this proof was super duper hard. It's like 10 pages and it's quite a bit of work. And it's quite an in-depth calculation to figure out exactly how to prove this lower bound. And we didn't realize this like sort of very natural correspondence between the two objects. We were just kind of soldering through the details, I guess you could say. So this is kind of why I like this result so much, is because I worked so hard on the last one. And now finally, our proof, where our simplified proof kind of came from was another recent paper that involved myself from a few years ago that I won't go into, but it sort of had some closely related proof techniques, and we sort of realized like, oh, these things could actually simplify this pebbling thing that's been bothering us for a while. Okay, cool. Yeah, so I'm going to move on to the proof next. I'll be able to do the entire proof, but now's a good time to pause to see if there's any questions or anything.
I have one more for the black pebbling.
Yeah.
Black pebbling number. So it's like looks like some kind of max cut in a graph, or some kind of cut in a graph, or is there a relationship to
that? Not really, because things can be done asymmetrically. I could always, it's not clear, kind of, it is. I think that maybe the cut might be a lower bound, but it's not a very good one. There are constant degree graphs which have very high pebbling number and like low cut number, for example. Yeah. So so it's a lower bound maybe, but it's not a like a vertex cut, I guess. Yeah. It's a lower bound, but it's somehow not too related. Yeah.
Okay.
Anything else?
I think people don't be shy. Yeah. Ask questions.
Excuse me, could you please show how we turn a graph to a propositional formula one more time, please?
Oh yeah, sure, no worries. Yeah, so right here. So here's our graph. So intuitively, you should think of the formula as just saying the following: all the sources of the graph have to be true. The sink of the graph has to be false. And then for every node, if all the you have a clause which says if the predecessors of the node are true, then that node is true. So like, for example, U3, I've got this clause right here which says, okay, if U5 and U6 are true, then U3 has to be true. Is that good?
Yes, thank you.
Okay. Anything else?
I have one question.
Yeah.
So the uniqueness of sink is just so that this number is well defined, right?
Yeah, I mean, like you could, of course, naturally. I mean, the real reason that I make the sink unique is because it makes this formula really simple to define. Like it's clearly unsatisfiable. You could define pebbling numbers for graphs with multiple sinks and say, I have to put pebbles on all the sinks. But then this encoding doesn't really make sense as a propositional formula, because I would only have to refute one of the sinks, not all of them. You know what I mean? So it's mostly a convenience for proof complexity for the proof encoding, basically.
Okay.
All right, then let's see the proof. Okay, cool. All right, so just to remember, this is what we're going to prove now. So if you have an NS proof of this pebbling formula with degree D and size S, then we'll get a reversible pebbling strategy using D pebbles in time S. So here's some notation I'm going to use throughout the proof. So for simplicity, we can just fix the field to be F2. All the fields kind of work the same, but it's just, if you want to be concrete, you just sort of makes your life easier. We'll fix a graph with a unique sink. For any subset of the vertices, I'm gonna like associate the subset x sub s to be just the product of all the variables which are occurring in S. Okay, and then the pred of V is just going to be the set of predecessors of the V, and then finally, just to make it super explicit, each of these internal axioms for the pebbling formulas, the ones that say, if the predecessors are true, then then V is true. When we convert it to a polynomial, it's going to look like this. It's going to have like the product of all of the variables in the predecessors multiplied by 1 minus the target, right? Just to make that super explicit. Okay, so how do we convert a pebbling into a Nullstellensatz proof? Well, it turns out to be like really, really, really easy, and it's really frustrating that it's kind of frustratingly easy, in fact. So let's suppose that we had a reversible pebbling of the graph. So this is the sequence of the pebble configurations. And of course, the last guy is going to be, this is going to be the empty set because we have to clean the graph after. Okay. So I'm going to let T prime be the first time where the sink gets pebbled. Okay. And we want to make a Nullstellensatz refutation. So that means we want a polynomial for every vertex, and also like a final polynomial, this sink polynomial, such that if I multiply G0 by the sink axiom and the G sub V by these A sub Vs, which I just defined, these are just the clauses, the internal clause axioms, then I get exactly 1. Okay. And the main idea is totally transparent. All we're going to do is we're going to identify every monomial in the proof with the with the configuration on the graph that has pebbles on the corresponding subset. So if that monomial occurs in the proof when we fully expand it out, then that's going to correspond to that's going to be the corresponding pebbling configuration. So it's kind of cool because like a pebbling configuration has to be ordered, right? You start from the empty and you go to a thing where the sink is pebbled, and then you come back and everything has natural ordering. Whereas there's no natural ordering in a Nullstellensatz refutation. And so what this correspondence is telling you is like, I can give you like an unordered reversible pebbling thing, and somehow they all cancel out, and then you can order them in a way so that it works out to be a valid strategy. So what's the proof? Well, the proof is like entirely contained within this picture. So here's a picture of the graph. So this is the pebbling. This is the configuration of pebbles at time I minus 1. This is the configuration of pebbles at time I. Okay, and let's say that we wanted to put a pebble on this vertex at this time. Okay, so all the predecessors of V are pebbled, and then at time pi we put a pebble on V. And then of course there's going to be some other set of nodes, which I'm going to call R sub I. These are the nodes that are already pebbled, but they're disjoint from the predecessors. These are just whatever the other junk that's hanging out in the graph. Okay. Well, what we're going to do is we're going to give a Nullstellensatz proof of this difference. So the product of all of the variables that occur in P sub I minus the product of all the variables that occur in P sub I minus 1 minus the product of all the variables that occur in P sub I. Okay. It's just easiest to see this by working it out, I think. What is x sub P sub I? Remember, this is the product of all the variables which have this pebbling configuration. Well, it's all the guys in R sub I with all the predecessors of V sub I. Those are all the pebbles that are there. What's P sub I? Well, that's these guys, and then I also have x V sub I because I placed a pebble there. So if I subtract them, well, I just factor out x R sub I, and I have the predecessors, and then I have 1 minus x sub V. But this term right here, this is exactly the axiom for A sub V sub I, right? So the Nullstellensatz proof of the difference of these two configurations is trivial. You just take that axiom and you multiply it by all the pebbles that are just hanging out in that at that point in time, right? And of course, if you removed a pebble, you would just multiply it by -1 because it's just going to flip the order of which guy gets the pebble. Okay. Well, now the proof is done. Like, that's it. So what do? Well, you take the pebbling configuration at time t prime, you delete s from it, and you multiply it by x sub s. That's the sinc axiom. And then for every other time, you just multiply this axiom by whatever, extra set of pebbles gets multiplied. Like whatever the extra guys that were hanging around that were not part of the predecessors. And then by what we just argued, this is going to be the sum of these xp sub i's minus xpi. And that, of course, telescopes. So we just get p0 minus pt prime. P0, this is 1. It's the empty set, right? There's no pebbles at time p0. Pt sub prime, that's just right here. So those two also cancel out. I think there's a mistake on the slides. It should be x sub p and x sub p sub t. So these just cancel out. And this is equal to 1. So it's just 1. So that's it. The degree is clearly the number of pebbles that we used, right? I never used more than the degree of the pebble I never used degree higher than the pebbles, the number of pebbles. And the size, well, how many monomials did I have? Well, remember that this A sub V sub I, this is of the form 1 minus x sub Vi times x of the predecessors, right? And so in other words, and then this guy right here gets multiplied by a single monomial. So for every step in the proof, I get exactly 2 monomials being generated from it. One from this and one from this. So the size is just 2 times t prime plus 1, and that's exactly the length of the proof. And this is now why we made you run the proof in reverse, right? Because it doubled the time. Okay. All right. So that's it. So now question?
Yeah, I wanted to. So what were you doing before? So what
So before we directly proved lower bounds on the complexity of Nullstellensatz refutations. So there's a whole algebraic tool set that you can use to do this, which involved creating some low degree functions and the dual space, and then proving that these things are anyways, it's work. Let's put it that way. So it was totally not like this. We didn't think about the combinatorics. It was so much. It was the proof was quite intense actually. We didn't just try to sit down and look combinatorially at what these proofs actually look like.
Cool.
Yeah. So we can also do the reverse direction. Well, I mean, and this is also really simple. We basically just take the last argument and invert it, right? The correspondence is still going to hold true. But now this is kind of the interesting direction, because we're going to, this is where this thing that I mentioned earlier happens, where we kind of, line up this, have these, what do you call it? The unordered proof is going to get reordered into an actual reversible pebbling of the graph. Okay. So what happens here? Well, let's start. So we're going to start with a degree D Nullstellensatz refutation. And now I'm going to assume, without loss of generality, that the thing is multilinear. I'm kind of hand waving away the use of the xi squared minus xi axioms. Let me just say that those can be dealt with. I don't want to get into the details of that. That's just weeds. And again, we'll be working over F2 just for simplicity. And now what are we going to do? Well, let's let P sub D be the set of all D subsets of the vertices. Think about these as being all the pebbling configurations on V with at most D pebbles. And I'm going to create what I'll call a configuration graph on this from the proof. Okay. And then on the configuration graph, I'll be able to extract a pebbling strategy very naturally. Okay. So what's the definition of this graph? Well, I have my my refutation up here. Intuitively, all I'm doing is I'm just inverting the previous proof. So in the previous proof, what did I do? Well, each one of these axioms had a single monomial multiplied by it. So I'm just going to extract out all the monomials and create a pebbling move that corresponds to that monomial, and then just work them all out, and then it will just turn out there will be a reversible pebbling strategy because everything has to cancel out, basically. So to do it formally, let's just pull out a monomial, x sub w. Okay, w is contained in v. So let's just pick any one of these vertices, pick the polynomial that I'm multiplying by it in the proof, and let's extract out the monomial that corresponds to it. And we'll say that it doesn't contain x sub v or its predecessors. Okay. And now for every such monomial, what I'm going to do is I'll add the edge between these two configurations in this configuration graph. So you should just think of this as just inverting that step in the previous proof. I'm just picking out a monomial and I'm creating like a reversible pebbling move, one candidate reversible pebbling move in the strategy that I'm creating. So I'm going to do this for every such monomial. And what you should observe is that, well, clearly every edge in this graph corresponds directly to a reversible pebbling move, right? Because all the predecessors are here, and then I just put a pebble on V here, right? And of course, also every edge corresponds to a single monomial, which is going to occur in the resulting proof, right? Each one of these x sub w's. And also observe that this graph C, it might be a multi-graph because I might have the same monomial appearing a bunch of times, right? I might put the same edge there. I'm going to do that. I'm going to keep adding in those edges a bunch. However, it's also bipartite. And the reason for that is because I'm always connecting, you can divide all the pebbling configurations into odd and even sets, and I'm only ever connecting things of the opposite parity, right? So I can divide the graph into two sets, the ones with odd number of pebbles and even number of pebbles, and all the edges go across the middle, right? So it's just this is a pretty simple bipartite graph. Okay. So now we have a graph. Edges correspond to pebbling moves. So a path in the graph corresponds to a pebbling sequence. So what we're going to do is we're going to try and find a path from the empty set to a node that has the sync vertex in it. And to do this, we'll use this main claim, which is simple. I'll just postpone the proof for a second. If you pick any configuration of D pebbles such that the sync is not in U, then if U is empty, then I claim that the number of edges that will be incident to U is odd. And if U is not empty, then the number of edges incident to U will be even in this graph that I've created. Intuitively, the reason for this is because of the Nullstellensatz refutation, all the monomials have to cancel out. Each sub U corresponds to a monomial x sub U, and they also and all those monomials are going to disappear when I expand everything out, and so they're all going to have to be even except for the monomial that corresponds to the empty set, which is going to be 1. But once we have this claim,
Robert, sorry, what is PD again?
P sub D is just the collection of all subsets.
Okay, yeah.
Just the vertex set of this configuration.
Mm-hmm. Okay.
Yeah. Okay. Now, once we have this claim, we're basically done. We can get a reversible pebbling pretty much immediately. So how do you do it? Well, I said it just a second ago. We want to find a path from that starts at the empty set and goes to some set that contains the sync node. And by the way we constructed the graph, every step corresponds to a legal pebbling move. Well, just pick the connected component that contains the empty set, okay? And then I claim that there's going to be there's going to be some node in there that contains S, that contains the sync, okay? So why is that true? Well, I mean, the reason is just a parity argument, right? We know the graph is bipartite, and then I know up here that if all of the guys in this connected component didn't have S, well then I would only have a single node with odd degree, right? Because all the other ones are going to have even degree. And that's obviously impossible. If I sum up all the degrees here and all the degrees here, they have to be the same. They have to have the same parity. So by a parity argument, we just immediately get that there's going to be some H, some configuration U in this connected subset that contains the sink. And now that we have this guy, well, then we have the reversible pebbling strategy, right? We just start at the empty set, walk to whatever U is. As we defined the thing, that is going to be a legal pebbling strategy. And then so we do that for the first half, and then we just reverse it on the other side in order to clean the graph off. And that's the reversible pebbling strategy. So we're going to use at most D pebbles by definition, because every configuration has at most D nodes in it. So now why does the length happen? Well, it's again because every edge is going to correspond to two monomials in the proof. If I look at this axiom, A sub V, you know, it looks like X sub pred times 1 minus X sub V. And so when I multiply any monomial by this, which corresponds to an edge, I'm going to get two monomials in the resulting proof. So when I double up, so the length of this thing corresponds to, like, you know, 2 times the number of monomials, which is exactly the size of the proof. Okay, so this is it. It's just basically it's just the natural inversion of the previous argument. So now let's finally prove this claim, which is also easy. This little parity claim. So if U is empty, then the number of U edges is odd, and if U is not empty, then the number of edges is even. Okay. So here's the proof. So first, let's suppose that U is not empty, and of course that S is not there. And let's remember what the Nullstellensatz proof looks like. It's just this guy right here. Now, how did we create the edges incident to U? Well, every edge that was incident to U corresponds to a monomial that's in the G, in some G sub V for some V, right? So one of these guys is going to get multiplied by this guy. That's going to correspond to a pebbling move. And then I added an edge entering U if either a pebble was placed or removed from that pebbling configuration corresponding there. Well, now I know that if I count up all the edges incident to U, those are all monomials in this proof. And if I look at the right-hand side, all those monomials disappear. So there must be an even number of them because the field is F2. And this is where I'm using the simplifying thing. Over FQ, it's just as easy. And on the other case, if U is empty, well, I mean, you know, it doesn't cancel. You know, it's 1. So there must be an odd number of occurrences of it. And so the number of U edges for this one must also be odd. And that's it. Okay, so there you go. That's the whole very simple proof. This theorem. So in the last couple of minutes, I'm going to talk about some of the trade-offs we can get. But are there any questions that I can answer first?
So a stupid question, I guess.
Yep.
So the degree. So you said that the degree of the sink is odd, right? Or
yep.
So why is that? Very simple.
Let me just go back to it. So the sink is going to be any. Wait, the degree of the sink is going to be odd. Sorry, maybe I didn't understand. The degree of the empty set is going to be odd, is what I said.
Yeah, no, the degree of the empty set is odd. So yeah. Can you show then again how do you get this connected component containing the sink part? Yes,
sure, yeah. Here it is.
Stupid, I missed it.
Yeah, okay. So so you start with the connected component that contains the empty set.
Yeah.
And this claim only holds for sets that don't contain the sink node. Okay. So
so this is the okay. So
yeah.
claim,
so it's non-constructive. Okay. Yeah.
I'm just this I guess my question was about the about this, that they do not contain the sink. Okay.
Yeah, nothing here contains the sink, so the parities have to be, well, the parities have to be even by handshaking, and so. Yeah, cool.
And yeah, and the reason you're looking, it says that do not contain the sink only is so somehow. Okay, I'll think about it.
Yeah, the reason that I'm looking, I mean, I can answer. It's just that, like, because the sets that don't contain the sink are exactly the ones that get multiplied by these axioms here. The ones that contain the sink all get multiplied by this x of s right here.
Okay.
Yeah.
Right. Yeah, I forgot that you separated them. Yes, that's true.
Cool. Any other questions I can answer?
Yeah, I've got a question. Maybe
yeah.
Very stupid one, but is there any connection with the? I've been late, by the way. Is there any connection between your talk and Hilbert's Nullstellensatz theorem?
Yeah. Yeah, that was like, yeah, sorry, you were late. So that was like one of the first slides. Yeah, so the Nullstellensatz proof system is like defined by basically it's like defined by, like the reason it's a complete proof system is Hilbert's Nullstellensatz. Yeah.
Okay. Thanks.
Yeah, yeah, no worries. It's cool. Anything else? Okay, so in the last 10 minutes, let's talk about some trade-off results. Okay, so we're going to talk about some of the trade-offs. And by this theorem that we just proved, we can just get them from trade-offs for reversible pebbling. All the trade-offs that we get are assembled by basically combining and then massaging some of the trade-offs that are already known in the literature. So this reversible pebbling game, because reversible computation was kind of a big thing, and also these pebbling games were studied a lot in the 80s for things like register allocation and these very like low-level algorithms in computer systems. So there was a lot of results done on time-space trade-offs for these things. So we're able to sort of take those and massage them to get the trade-offs for the Nullstellensatz proofs that we find that we actually are interested in. So let me tell you what sort of the ideal schema of what the trade-off result is going to look like. So what we want to show is that there's families of good graphs, G sub n, such that first G sub n can be pebbled with, say, D1 pebbles, where D1 you should think of as being very small, but of course it's going to require lots of time in order to do that. And now on the other hand, G sub n can be pebbled in near linear time, because if I use, n pebbles, like the number of nodes in the graph, I can obviously do it in linear time. So maybe I can get within near linear time if I just increase the number of pebbles somewhat. And then finally prove that if we scale down the number of pebbles that we use, if we pebble using fewer than D2 of pebbles, well, then we need to hit that near maximal time that we should have used in order to pebble it with D1 pebbles. Okay. So maybe that's just it in words. It's kind of easier to think about it kind of as a graph. I mean, you can imagine that there's kind of two thresholds here. So first we have this D1 of the proof. And of course we can pebble, we can come up with a proof in size n to the D1 just by deriving all the monomials of size at most D1. Okay. And then on the other hand, we have this second degree D2, and we would like for it to say that, we can do it in nearly linear time as long as the degree is much higher. And then the question is, what goes on in the middle? Well, what happens in the middle, right? It's very simple. So like, are there situations where you could get like a smooth trade-off? Maybe as you smoothly increase the number smoothly increase the degree or the number of pebbles, the number of size also decreases smoothly. Or maybe we can prove that there are like sharp trade-offs. So as I increase the degree, suddenly like it doesn't help me prove it at all until I get to some point in time where, all of a sudden adding a few extra pebbles really lets me decrease the size. Yeah, is there a question?
No, sorry, no.
Oh, okay, cool. Or maybe just totally crazy things happen. We really just have no idea what happens kind of dynamically in the middle. So I'll sort of just say 3 of the trade-off results that we get. So first, what we show is that this kind of sharp trade-off actually happens. So it's really quite surprising. So by using this sort of family of graphs that was defined in the 80s, which are complicated, I don't want to get into the definition of them. What we can show is that there's proofs in degree D1, which is like polynomial in n, like n to the end of the 6th. Okay, and size, of course, roughly that, n to the end of the 6th. However, if I increase the degree by a polynomial factor, like n to the 6th, well, then all of a sudden I can decrease the size to nearly linear. However, if I shave even a log factor off of this higher degree, the size of the proof is still going to be exponential. It's still going to be nearly, in fact, like as the tight lower bound, like n to the end of the 1/6. So up to a log factor of pebbles, like changing the number of pebbles that you have by a log factor can increase the amount of time that you need to spend from linear to exponential, to nearly maximal, in fact. Like you may as well never use any more pebbles and just go back to the stupid thing where you just try everything. Okay. We can also get, I mean, one thing that you might quibble with is that like both of these numbers are already kind of high for the Nullstellensatz degree. Like they're both like polynomial in n. Like what about low degree refutations, right? And we can handle that regime as well. So we can and still get very sort of sharp trade-offs. So we can range now all the way from D1, which is like roughly log squared of n. Okay, so now we're getting close to the order 1 pebbles almost, where of course we require lots of time. And yet if we increase D1 by a nearly maximal factor, right, like n over log n. Okay, well now we can again get to nearly linear. This should be the size is still like nearly linear. Okay. And yet, once again, if we decrease the degree by a log factor, actually even less than a log factor, like a log to the epsilon factor for some epsilon-less. So here we get a trade-off where the difference between the degrees is like of nearly maximal range, like all the way from almost constant to, well, I mean, it has to be super constant in order to get interesting size lower bounds, but all the way from slightly super constant to nearly linear. Okay, so when D1 is, there's still pebbling strategies with log squared n pebbles now. And in order to get linear size, linear size refutations here, you need to add you can get this by adding by multiplying by like a linear factor of pebbles. So you need to go all the way almost to n pebbles in order to get a nearly linear time. However, once again, if you lose just a log factor in the number of pebbles here, well, then you still have to pay like a super polynomial blow up in the length of time. And this lower bound like incurs like all the way down, all the way to D1 of log n. And now the lower bound isn't quantitatively as strong. It's not, we would like to have like n to the log squared n here. That would be sort of tight. We only get n to the log n, but yeah. And then finally, these
and when you draw a straight line, is it really a straight line? Meaning just
we don't really know for these two results. We really don't know any more of the dynamics between the two. Like intuitively, it should increase, perhaps, right? I actually think for this result, it's really almost tight, actually, right? Like because it's really like n to the D1. Yeah. So for this result, the straight line is actually like correct. It's only off by a little tiny gap here, and that's probably a loss due to the techniques, not anything major.
So just this log n, extra log n, yeah?
It's just that extra log n. Yeah, exactly. For this one, probably there should be some more interesting dynamics happening here, but we don't really understand what the dynamics are. This is kind of a complicated graph that I don't want to get into defining. So yeah. But we do get some smooth trade-offs, to answer that question, in a different way. So we can actually exhibit some graphs that do give a sort of smoother transition. So so for the if you start with these permutation graphs, which are simple enough that I'll actually like define them next, because they're on the poster for my talk, so I have to define them. When you, for any epsilon, any arbitrarily small epsilon, there is a proof with degree d1, like n to the epsilon, and not maximal time, but time like n to the n squared minus epsilon. So this gets, as epsilon tends to 0, the worst case time is going to be quadratic. Okay. And then if you go to d2, as epsilon tends to 1, well, then we get a linear time pebbling using a linear number of pebbles. And in fact, you can prove that this trade-off here is totally smooth. Like, as I add in an extra epsilon factor of pebbles, the time decays by an n to the epsilon factor. Okay, so there are actually interesting families of graphs which don't just have these sort of sharp thresholds happening. It's actually smooth. So the dynamics can be more interesting than just that. So I can define these graphs for you. I had a little short proof, but we're going a little bit long on time, so maybe I won't do it. But I will at least define the permutation graphs because I think that they're nice objects. So what's a permutation graph? Well, it's sort of it's one of the simplest graphs you can kind of imagine. So you fix a permutation, and the graph g sub pi is going to have 2 n vertices, and it's just going to encode the permutation. So I'll have 2 paths of n vertices on the top and bottom, and then I just match the bottom n vertices to the top one according to the permutation. So I add an edge from I on the bottom guy to pi sub I on the top guy. Okay, and then in terms of pebbling, well, this is my only source, and my goal is to get a node to this sink right here. And so intuitively, in order to do this, I'm going to have to like move pebbles around on the bottom. Like I want to move some pebbles across the top here. And in order to do that, I have to like shift pebbles down around on the bottom in order to like make sure that the correct predecessor is pebbled so that I can shuffle it along, right? And the particular family of permutations, which gives you this really nice, smooth trade-off, is also very simple to describe. It's just bit reversals. So if you let n, if n's a power of 2, then just let pi sub I be mapped to the reverse of the binary encoding of whatever I is. Okay, so I mean, here's an example when k is 3, I guess. So you can see here like 0, 1, 1 here. Well, I mean, the bit reversal of 0, 1, 1 is 1, 0, 0. So it gets mapped to that. And then there's some fixed points here. 0, 1, the ones that are symmetric, they of course get mapped to themselves, and the later ones get mapped to earlier ones. And it's exactly these graphs that are going to have these very, very smooth trade-offs. And intuitively, it kind of makes sense, right? If you give me tons of pebbles, like n pebbles, well, then I can just put a pebble everywhere on the bottom, and then I can just pebble the top like it doesn't even matter. You know what I mean? Like I can just move pebbles along and I can totally ignore it. But the second that I remove the second I have less pebbles, like asymptotically less pebbles, maybe square root of n pebbles, well, now I've got to like somehow move them around on the bottom. Like I'm going to have to be constantly moving things around on the bottom in order to simulate the right pebbling strategy on the top. And so this was so Lengauer and Tarjan proved back in '82 actually that this smooth trade-off existed and was tight for the black pebbling. So that's where you can remove pebbles for free, not with reversible. And of course we need it for reversible. So we do actually have to do something here. So in black pebbling, we can always remove them. In reversible pebbling, this is not true. So the lower bound is still okay because black pebbling is like weaker than reversible pebbling. So the only thing we need to modify is the upper bound. I don't really have time to talk about, I guess, how we do that, but maybe I'll just skip over that and I'll just say sort of what the intuition is. all the intuition is just the following. So here's the formal theorem that we're able to prove. So if S is your number of pebbles that you're allowed to use, then we can reversibly pebble this bit reversal graph with S pebbles in time n squared over S with this like k to the 2 to the k factor blow up. And this k to the 2 to the k is why I only stated the trade-off for like n to the epsilon, because then this kind of, we don't worry about it. It just kind of gets absorbed into the big O. And the intuition for how this works is it's pretty simple. It's kind of like what you would expect to happen, in fact. What we do is we just leave pebbles on the bottom at equally spaced increments. So I'm going to leave them roughly n to the root k nodes apart. And then whenever I need to shift a pebble along on the top, I find its closest predecessor on the bottom, and then just pebble up to the predecessor I need to, put it on the top, and then move it down. And then I just have to repeatedly do that. So for every pebble move that happens on the top, I have to pay, roughly an n to the 1 over k factor in order to move it on the bottom. And this turns out to work out, I guess, is the intuition. There's some more work that has to get into this, but yeah, maybe I won't mention it. Okay, cool. Well, that's so here's just a picture of the trade-off graph again, just to remember. This is sort of a smooth trade-off, and this line, of course, is sort of depending on epsilon, which is just what I said a second ago in words. So that's basically everything that I wanted to say today. So let me just sort of give a quick conclusion. So we gave a new characterization of this combinatorial quantity using a proof system and an algebraic proof system, which of course occurs in tons and tons and tons of different situations. So I think it's very natural to ask whether or not other quantities can be captured in this way, right? It seems that length in proof complexity very naturally corresponds to this combinatorial quantity that's occurred in tons of contexts. So maybe you can capture other combinatorial things this way, and maybe we can either get new results in combinatorics or new results in proof complexity by thinking about it this way. Sort of one of the natural, the natural open problem that's kind of left here is proving, I think, sharper trade-offs for reversible pebbling. So if you look back at these graphs that I had there a second ago, oops. Oh, okay. Well, that's okay. If you go back to these graphs, you can see that it's just what I said, what Andre was asking. This line is really like a straight line in our trade-offs. And so the dynamics of what's happening here is for one thing, not very well understood. Like, should it actually be a straight line? It really feels like there should be a more smooth trade-off, or at least we should have some understanding of the dynamics of what's going on as the degree increases compared to the size. And the second thing, which is a natural question, is to see how much you can decrease the gap before this huge sharp spike in size has to increase. So for black pebbling, in fact, if you give me the ability to remove pebbles whenever I want, it's known that if you just keep one pebble and remove it, then that can cause a super polynomial increase in time. There's incredibly sharp trade-offs for black pebbling, but we do not have the same trade-offs for reversible pebbling. We don't know how to prove it. So it's a very natural question whether or not such trade-offs even exist. And yeah, that's it. So yeah, thanks for having me. Yeah, I can answer any questions.
Great, thanks a lot, Robert. That was really interesting. Yeah, I guess you answered a couple of questions with the list that I had with the list of open questions. So all this result, apparently, this Tarjan that you cited, all of them had a sharp kind of statements for this smooth transition as well, right?
Yeah, for this, this LT, this Lengauer-Tarjan one is definitely sharp. This n squared over S is basically sharp. I mean, maybe like the multiplicative terms aren't sharp, but like, yeah, it's essentially sharp. For the other ones are very much not sharp. For these other graphs, like these weird stacks of super concentrators and these Carlson-Savage graphs, whatever they are, the graphs themselves are like incredibly complicated to define. Like they're not like the permutation graph. I couldn't just give a definition in like 1 minute. And that really, of course, makes proving the trade-off more complicated.
And the black pebbling, does it, because you said at some point, I think something, but the black pebbling, does it have some kind of nice interpretations in other ways as you were suggesting?
Yeah, I don't know of any characterization of it in proof complexity like this. Now I think that there should be one. I didn't think of it before, but now I absolutely think that there should be one. But somehow, I mean, obviously what you need is some proof system that sort of mimics the ability to forget in this black pebbling way. Maybe there's like some sort of natural way to modify Nullstellensatz. To me, this relationship between Nullstellensatz and reversible pebbling is just magical. Like everything just lines up perfectly for everything to work out. So it's kind of hard to imagine it's natural to imagine if there's a simple modification that would lead to a characterization like that. Yeah, I really don't know, but it's a very interesting question, kind of conceptually.
Yeah, cool. It's very surprising. I didn't expect that when I read the title.
Yeah.
Definitely.
Yeah, I mean, it really surprised me too, especially since, like I said, proving the lower bound was so hard before, and then so when we figured it out, it was really quite a surprise to me as well.
Also, I had a question about this trivial graph, this path. So, how does this trade-off behaves for this path?
Right, interesting. Good. That was actually in the proof that I was going to do, but we ran a little short on time. So here's the exact statement. See, I'm ready. I'm ready for your questions. So basically, it works like this. You can, for every single k, you can reversibly pebble the path graph in time like 2 to the k to the n with like 2 to the k times 1 n to the 1 over k pebbles. So like the intuitive reason for this is sort of the argument that I gave, the argument that I hand waved a little bit for the permutation graph. So to do it in log n pebbles, it's very easy. You just first you pebble the midpoint, right? And then you undo the first half to clean it off, and then you do the second half. So obviously you're going to increase the number of pebbles that you're doing by 1, but you've got to undo and redo some work. So when you work out what the recursion tree is, the time works out to be roughly in the log 3. So in order to get this smoother trade-off, well, you can think about this as like, spiking one place. Just spike a bunch of places instead, and then pebble and unpebble and pebble and unpebble, and then you can get I state it in terms of an integer parameter. You can get an even smoother trade-off if you wanted for large n.
Okay. And are there any generalization of this this graph and this permutation graph that would have larger polynomials?
I think that like a stack of permutation graphs makes a lot of sense. Like if you just took this and you stacked another bit reversal on top of it, and then another bit reversal on top of it, intuitively you would have to increase the things by a factor of the depth of the number of guys, right?
Because this looks like a second kind of like a square of a path graph, not a square, but 2 levels of a path graph.
Yeah, exactly. Yeah, like D levels of a path graph. Yeah. So with a sort of sufficiently complicated thing in the middle to make pebbling the next layer difficult. I think that should work, but yeah, I haven't worked it out.
Okay. Cool.
Cool. Anything else I can answer?
People are thanking you in the chat.
Yeah, thank you.
Cool. I guess if not, then yeah, thanks a lot, Robert. It was really interesting for me, definitely. I hope for the students as well.
Cool. Yeah. Again, thanks for having me.